So today's topic is sequences and series. A sequence is nothing more than an ordered progression of numbers. So when we want to write a sequence, a lot of times we use our curly brackets, and then we have a list of numbers that are following that curly bracket. Bless you. So I have two examples of a sequence listed. One of them is a finite sequence, which means that it ends. It has a final term. It started out with 3, and then it was 6, then 9, then 12, then 15, and then we're done. But we also have an infinite sequence, and that one started with 4 and went to 8, then 12, then 16, then 20, and then it has, is it called an ellipsis? The dot, dot, dot? Correct me if I'm wrong. Okay. And that means that we continue on in like manner forever and ever and ever. So it's infinite. Keeps going. So far, so good? Okay, so when we're talking about a sequence, this ordered progression of numbers, we have two types of formulas that we can use to generate a sequence. One of them is called an explicit formula. Okay, it's just basically you plug in a number, you get something out. The other one is called a recursive formula, and that one depends on what happened before in order to create the next. So the explicit formula is plug in positive integers to generate the terms, and we have an example of one that we want to generate the sequence for. So we're starting out with a sub n. A sub n is the common variable that we use, a letter plus a subscript, and that subscript is going to help us keep track of which term we're talking about. So when we want the first term, a sub 1, it stands for the first term, we're going to plug in what everywhere we see n? A 1. So our first term will be 1 squared plus 1, which is 2. Okay? Just like plug and chug, substitution. So then when we want our second term, we're going to take and let n be 2, right? And we'll take 2 and square it and add 1, and we get 5. To generate our third term, we're substituting 3 in everywhere we see n. So a sub 3 is 3 squared plus 1, which is 10. And finally, we want our fourth term. So everywhere we see n, we're going to plug in a 4. And we get 17. So we have the first 4 terms of that explicitly defined sequence. Questions on that one? Okay. Then the recursive formula says I'm going to I have a reoccurring theme here. Okay. I have to be able to base things on the previous stuff. So the recursive formula is going to look like it's got more going on with it. And we have to do a double substitution here. One, we have to substitute a number in for n to find a term number. But then the second thing we have to do is actually substitute a value of a term in to find out the final answer. So when we're looking at this recursive formula, we don't have to generate the first term because it told us what it is. That first term is -10. So if I'm asking you to find the first 4 terms of this, you already know one of them. You only have to find 3 others. So far, so good? Okay, so when we want to find the second term, what are we going to do? Plug in 2 everywhere we see n. So we want the second term, b sub 2. That means that we need to plug in a 2 again when we see n. But what is 2 minus 1? 1. So b sub 2 is going to be the same thing as b sub 1 plus 5. So that was our first substitution. We just substituted 1 in for n. But now we have to substitute the first term in for the first term, don't we? What was our first term? negative 10. So we're going to take negative 10 and add 5, and we will get, good. All right, now we want to find the third term. So what are we substituting everywhere we see n? A 3. So to find the third term, b sub 3, we're going to take b sub 3 minus 1 plus 5. But 3 minus 1 is b sub 2. b sub 2 was, so we're going to take negative 5 plus 5 and get 0. What about b sub 4? What's it going to be? 5. Why? Because it's the previous term plus 5. Does that make sense? So when you see something like this, I want the next term, but it's based on the previous term plus 5. Once you start to recognize that, you don't have to start plugging numbers in for n and then plugging in the term for its value, right, or its value for its term. You can just say, oh, wait a minute, I just need to take the previous term and add 5. Okay? So my previous term was negative 10. If I add 5, I get negative 5. If I add 5 to that, I get 0. If I add 5 to that, I get 5. If I add 5 to that, I'll get 10. If I add 5 to that, I'll get 15. Make sense? All right. Questions on this one? All right. This is the hardest concept for some reason. For some people, it was for me anyway. Okay, upper right corner now. Okay, we're in the upper right corner. This is not something we're going to ask you to do today beyond these examples. Okay? For some reason, our book likes to say, hey, let's generate a bunch of sequences, and let's actually generate the sequences isn't an issue because we're plugging numbers in to see what we get, right? But coming up with those sequences, if we the formula, the explicit or the recursive formula, when we have the sequence is a little tougher. And so we want to give you the tools to do that. So some of those tools come in section 9 or 8 or 9, whatever chapter we're in, the next section on arithmetic sequences, and then some will come in the next one, which is a geometric sequences. So rather than just give you a bunch of a toolbox with a bunch of tools in here and say build something, I'd rather show you how to use those tools first and then ask you to build something. Does that make sense? So we'll expose you to this today, and then we won't expect you to do a lot with this one, but then tomorrow we'll start in on the arithmetic, and Wednesday will be geometric. Okay? So we want an explicit definition for the nth term. Okay, unfortunately, that's a harder one to figure out. Recursive is very easy. Okay, so what do you notice about this first letter A, the sequence in letter A? Everything goes up by 4s. 1 plus 4 is 5, 5 plus 4 is 9, 9 plus 4 is 13, and so forth. Make sense? Okay, so we have to come up with some kind of sequence. Okay, so to find a term, we have to do something to something and something, right? Okay, we think it might be n plus 4, but that won't work, will it? Because if we want to generate the 20th term, or what have you, we have to be able to plug 20 in and get the right answer. Okay, we want to plug in 1 and get 1. We want to plug in 2 and get 5. We want to plug in 3 and get 9. See how this is tough? Easy when you have the formula, but not so easy when you have to generate it. Okay, so let's think about what's happening here. If I plug in 1 and I get 1, I plug in 2, I want to get 5, right? If I plug in 3, I want to get 9. What does that look like? A line. Mm-hmm. Negative 5 plus 4 would get us Negative, so negative 5 plus n plus 4. All right, let's see if that does the trick. All right, so if n is 1, okay, we're going to get 1 plus 4. Nope. So try negative 4. Negative 4 plus n plus 4. So so n is 1, we'll get 5. 5 plus a negative 4 is 1. All right, let's let n be 2. 2 plus 4 is 6. 6 minus 4 is 2. So that didn't quite work. First one worked, second one didn't. So maybe it's 4n. Okay, so let's try 4n. So 4n minus 4, 4n minus 3. So let's try n is 1 minus 3. Okay, so it's kind of a guess and check, isn't it? Once we see that it's linear, then what's its slope? We're rising 4 every time, right? So this looks a lot like y equals mx plus b, right? But what would b have to have been? Yeah. Okay, yes, sir. Good question. Now, do you see how hard this one was, the explicit definition? Okay. But David said, wait a minute, could we have done a recursive one? Okay. What was the first term? 1. So a sub 1 is 1. What would the next term be? So a sub n will be a sub n minus 1 plus 4. Do you see how easy that one is? Let's try it. First term is 1. We plug in 1 for the previous term, right? Add 4, we get 5. Put 5 in for the previous term, add 4, we get 9. So recursive formulas are not bad. There's just more to them, right? They look more complicated, but they're actually easier to generate. Does that make sense? Okay. Okay. So let's, okay, back to that thought. I'm sorry, one more time. Who said? With this one, the second one, or the first one? The second one? Okay. Okay, so if we're putting in 5, we'll say if our n is 5, then we have to know 5 minus 1, right, plus 4. So we have to know, if we want the 5th term, we have to know what was the 4th term, and then we're going to add 4 onto it. Okay, so this one's not great for generating a random term, but let's see what the 4th term was. 1, 2, 3, 4. So if we take 13 and substitute it in for the 4th term, will we get, when we add 4, the next term? 17. Okay? So recursives are easier to create, but they're hard to pick a big number and find the 25th term because it's based on the previous one. You have to know the 24th. Well, to find the 24th, you have to know the 23rd, and to find the 23rd, you have to know the 22nd term. Does that make sense? So there's benefits and detriments to both. All right, everybody satisfied with this as our explicit formula? Okay, and we weren't told that we had to find the recursive definition, but we also found the recursive definition. So explicit and recursive. All right, so we're ready for letter B? What do we notice about letter B? It's geometric, right? Everybody is changing by sum or a multiple of something. Multiple of 1/5. Okay, our first term is 1/5. Our second term is 1/25. Our third term is 1 over 125, right? And so on. Okay, 1 over 625, and so on. Okay, so how are we going to create, and again, this isn't something I'm going to expect you to master without more knowledge, but what do you think we can do to try to create the nth term? 1 over 5, and then 2 to the nth. Is everybody okay with that? Or 1/5 times n. Okay, so let's try either way. So if we try 1/5 times n, or 1 over 5 times n, okay, when we plug our first number in, 1, do we get 1/5 out? Okay, when we try our second term, we're going to put in 2 for n, do we get 1/25 out? We'll get 2/5. Okay, so that wasn't quite right. Let's try 1/5 to the nth. So this is guess and check at the moment because we don't have any other tools. Okay, so let's try 1/5 to the nth. When we plug in 1, do we get 1/5? When we plug in 2, do we get 1/25? Because 1 squared is 1 and 5 squared is 25. Gotcha. You were saying 1 over 5 to the n, or yes, to the n also works. Okay, they are both perfect. Does that make sense? Okay, so that was the explicit definition. Now let's think about recursive real quick, just for kicks and giggles. What's our first term? What's our next term going to be? Over 5, or times 1/5, right? And that one's easy to generate because you know the previous term and how the next one happens. Okay? Questions on these? Exposure only today. I'm not going to have you do a lot of practice with these. Okay, next piece then. Let's talk about factorial. Anybody remember factorial from last year? Okay. Our book defines it differently than I like to, because I like to use solid numbers, and theirs makes more sense going the opposite way when they're defining it. They define factorial as 1 times 2 times 3. So if you want n factorial, you take 1 times 2 times 3 times 4 times blah, 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 up to n minus 1 times n. Okay? Most of us think of it as going the opposite way because we have a number we're starting with. If we want 15 factorial, we're taking 15 times 14 times 13 times 12 times 11 and on down. Does that make sense? So I'm not going to ask you to ever formally write the definition of factorial, just to be able to use it. Okay, and most of us will go from the top down. All right, so special case, 0 factorial is 1, okay, even though there's nothing below it, right? And n factorial is only defined for positive integers. Okay, we can't use it with negatives, can't use it with decimals, only positive numbers, positive counting numbers. All right, so on your graphing calculator, and we're not going to actually use it for just a moment, but it's in the math probability section, and it's option number 4. So if you have a big number you need to find the factorial of, that's one way of getting there. On the TI-84 pluses, it's alpha, and then you choose F2, function 2, and then it's option 9. So this is a shortcut for these. Okay, now let's think about what these are then. So 5 factorial is probably one that we can do ourselves in our head. 5 factorial means we're taking 5 times 4 times 3 times 2 times 1, right? 5 times 4 is, 20 times 3 is, 60 times 2 is, 120 times 1 is 120. Okay? So mental math, we can probably do 5 factorial in our heads. All right. So we can do a race if you want, but I have a feeling that letter B is going to be faster manually by hand than it is to be on your calculator. Anybody want to race me? Oh, you already got the answer? Unfair. All right, because you had a head start. So let's think about what 8 factorial divided by 2 factorial times 6 factorial is. Okay? 8 factorial means that we're taking 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So far, so good? And 2 factorial means we're taking 2 times 1, and we're supposed to take that times 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. See anything in common in both the numerator and denominator? That's 6 factorial, right? So this 6 factorial will cancel with this 6 factorial. What is 8 divided by 2? And 4 times 7 is, so your answer is 28. So when you notice that you have a factorial in the denominator, you only have to write 8 times 7 times 6 factorial. The 6 factorials are going to cancel. 8 divided by 4 is, or 2 is 4, and take that times 7 and you've got your answer. Okay? Anybody want to race on the next one? I think it's faster to do it calculator-wise. It is 9 factorial divided by 3 factorial times 7 factorial. Okay? So 9 factorial, let's write it shortcut method. It's 9 times 8 times 7 factorial, right? We don't have to write the rest because we have a 7 factorial to cancel with, right? And we also have a 3 times a 2 times a 1. So those cancel. What's 9 divided by 3? And what is 8 divided by 4? Or 2. 9 divided by 3 is 3. 8 divided by 2 is 4. So what's my answer? Absolutely. Yep, same thing. Okay. The key here is if you do use your calculator, you have to do a 9 factorial divided by a parentheses 3 factorial times 7 factorial. Otherwise, it's going to take 9 factorial and divide it by 3 factorial, and then it will take that answer times 7 factorial. Okay, did everybody find that button on your calculator then? All right, let's do that real quick. So on the 84s, easy way to get there is alpha F2 and then choose 9. I don't know if this 83 will do that. So alpha F2 doesn't get me anything. Okay, oops. Okay, so we're going to have to plug in 9 factorial divided by, this is just long and tedious. Okay, so to get this, we do 9, go to the math, and then choose probability, and factorial is number 4. So that's 9 factorial. We'll hit the divide by and put in parentheses 3, so it's math probability 4. Yep. And then we're taking that times 7 factorial, so 7 math probability and 4. Close parentheses or don't, doesn't matter, and we get our answer. Okay? But you have a shortcut on the 84s if you do alpha and F2. That gets you the factorial quicker. All right, questions on these so far? All right, yes. Great question, yes. You will get to use the calculator on the whole test, and scientific or graphing, it doesn't matter, okay? Because they're going to require a lot of calculations that we're not going to ask you to do without. All right, so far so good? All right, so last example on this sheet. We want to know letter D. Okay, what in the heck is happening with n plus 1 factorial over n factorial? We could plug in numbers, okay? So let's try to plug in a number. Let's just to see a pattern. So what's your favorite number? 6. Okay, let's plug in a number in 6. All right, so if we say that n is 6, then what is 6 plus 1? 7. So that means that we're going to take 7 factorial and divide it by 6 factorial. What are we going to get? That would just be 7. Okay? So we plugged in 6 and we got 7 out. Let's pick another number. What's another favorite number? 7. So if we plug in 7, what are we going to get? 7 plus 1 is, so we'll have an 8 factorial over our 7 factorial, which is going to get us 8. Okay, so we're seeing a pattern here. What is n plus 1 factorial over n factorial? N plus 1, right? Whatever number that, one more than the number that you started with, right? So n plus 1. So another way to look at this is, how would I write this as a factorial? It would be n plus 1 times, what's 1 less than n plus 1? N times 1 less than n plus 1, or n minus 1, n minus 2, and so forth. Well, isn't that just n factorial? And if we divide it by n factorial, what's left? N plus 1. All right, make sense? So we've just made it much more abstract, but you could take it concrete and say, let's let n be 2, let's let n be 7, let's let n be 23, and see what happens. So far, so good? All right, so those were sequences in factorial. Now we have to talk about series. A series, go out of the way, go here, is a sum of a sequence. So we generate our sequence, and then we're asked to add them all up. Okay? A series is a sum of a sequence. And we like to use summation notation to write a series. Summation notation has that Greek letter sigma. It looks like a, kind of like an S, but really pointy. I don't know if I do. Maybe. And so we use this Greek letter sigma. It has two parts, well, actually 3 parts to it. It has an index, which is the starting point. It has an upper bound, an upper limit, and it has a lower limit. Okay? So, sorry. We're going to take these things and we're going to add them all up. So, first of all, there are actually three types of series. One of them is a finite series, which means that the sequence ended, right? And so we can add up all those terms and get our sum. We also have an nth partial sum. So if we have one that goes on forever, we can say, hey, what is the sum of the first 50 terms of this particular sequence that goes on and on and on forever? So far, so good? And then we also have infinite sequences, or infinite series, and that, depending on how the series is written, can converge on a specific number or go on forever and diverge. Okay, so far so good? Okay, so we want to find the sum of this series, or evaluate this series. Okay, now in many cases, instead of using the letter n, they use the letter I, but it could be k, j, it could be x, just depends on what variable they choose to use. But our index in this case is I. And it says that we're going to start at 1 and go to 5 and generate a sequence that we're going to add up to get our series. Okay, so let's let I be 1. That means a sub 1 would be 3 times 1, right, which is 3. And we're going to have to add the second term on. So if we let I be 2, a sub 2 is going to be 6, right? A sub 3 will be 9. A sub 4 will be 12. And a sub 5 will be 15. And then we're finished generating our sequence because we were told our upper limit was 5. Started at 1, went to 5, and generated all of our terms. So now we just have to add them up. So 3 plus 6 is, plus 9 is, plus 12 is 30, plus 15 is 45. So our answer is 45. So we have to generate the sequence first before we can evaluate the series. So far, so good? Okay. Next example. We want the sum as k goes from 3 to 6 of 1 plus k squared. So what term are we finding first? A sub 3, right? The third term of that particular sequence. Okay. So if we want the third term, what are we doing? Everywhere we see k, we put in a 3. So we're going to take 1 plus 3 squared, and we'll get 10. Now we have to find the fourth term of that sequence, right? And what are we going to get? 17. We take 1 plus 4 squared, 1 plus 16, and get 17. Now we have to find the fifth term of that sequence, and we'll get 26. And finally, the sixth term of that sequence will be 37. And so we would add them all up. 10 plus 17 plus 26 plus 37 is 90. Would you like to see how that one works on the calculator? Okay. I have the steps for a TI-83 on your sheet. Does anybody have an 83? No? Okay. So if you're on the 84s, the easy way to do this is to put in your function, or your alpha, F2. So press alpha and F2, and it's option 2. Look at how beautiful that is. Not so hard, right? Because when you press alpha F2 and choose 2, you get something that looks like this. And it's got a flashing cursor in this box, and it has an equal sign, and then it's got another box here, and another box here, and a box here. So what's going in the flashing cursor box? What's the easiest variable to get? X. Everybody okay with using X instead of K? You can do an alpha K and get K, but it's probably easier just to type your X in there. What goes in your next box? A 3. And then it's going to jump up here, and what goes in this box? A 6. And then what goes in this box? Yep. When you press enter, what do you get? 90. Okay, so great check. I want you to generate these series first, right, so that you have practice with it, and then generate the sequences and add them up so that you have practice with it. But can you see how this can be a savior on a ACT, especially when you're limited in time? Okay, questions on that one? All right, last example is an infinite sum. Okay, so here's our infinite sum. We're asked to find the sum as I goes from 1 to infinity of 3 over 10 to the I. Okay, so let's start generating that sequence. What's the first number we're going to plug in for I? 1. So we're going to take 3 and divide it by 10 to the first. That's our first term of our sequence. So what is 3 divided by 10? 3/10, right? 0.3. Everybody good with that? Okay, so that one's 0.3. Let's plug in 2. we're going to get 3 divided by 10 squared. What's 10 squared? 100. 3 divided by 100 is 3 hundredths, right? So 0.03. Our next term is going to be the third term, right? And I is 3. So a sub 3 will be 3 divided by 10 to the third is 1,000. How do we write that as a decimal? The little apostrophe is supposed to be a comma or an extra squiggly thing that doesn't belong there. Yeah, it's not meant to be there. A stray typo. Okay. So far, so good? Okay. So what do we notice? We can go on forever, right? But what's it going to become? If we add them all up, we get 0.3333333, right? And it keeps going forever. What number is that? 1/3. Okay? Questions on that one? All right. Assignment is straight from your little gold sheet.